So in this video, my thoughts are to continue with the shielding. If there are some viewers that, well, some participants, I would say, expressed interest in looking at a specific phenomenon with a motor running during acceleration, stopping at acceleration while accelerating, and there's a little bump that happens. And we replicated that. I couldn't find any inaccuracies, but we did hear the bump. Wondering if we should continue with that experiment. I'm thinking we might continue with the experiment. I'm thinking that we could probably do two things at one time, like kill two birds with one stone. Because since we need to run the motor anyway, we can test the shielding for that running motor, and at the same time we could be running a long-term experiment on the motor accuracy issue. So that's what I'm thinking. All right, I've got 9 people watching. All right, so I guess I'll go ahead and get started. All right, so we have let's see, we have 2 routers that should provide some noise, EMI, electromotive force, electromagnetic interference. This is a high-powered 3 horsepower router. This is a smaller router, and it's a Ryobi, so we can test to see the difference in each EMI. And just as a disclaimer before I get started, the experiments that I'm conducting here, well, the disclaimer is, like, be very careful if you're going to do them. Don't do them at home. But I also have to say that I have little experience in shielding. I recommend shielding, and I recommend all kinds of things, but that's all based on theory and based on what I've seen on the internet. These are experiments to confirm or explore shielding, so I can learn a little bit better, and I invite you guys to enjoy the experiments with me. In the previous to the last, I think it was on Tuesday of last week, we ran this router, and the router, it's loud. So whenever I run the router, I will always do a countdown so you guys can turn your volumes down, or I can potentially mute the sound. I don't know if I should do that because it doesn't really show I guess it doesn't help you understand that it's actually running or not. So I don't know, but it's loud, so just be aware of that. So I'll do a countdown. All right, so I had a motor connected, which is in here, I think. Yes, it's tangled like everything else in my garage. Now I'm going to set up my phone so I can see the comments, and I'm going to need to plug in my phone as well. I'm going to hit this. If I don't look where I'm going, I'm going to hit that camera every single time. All right. Oh, I have the wrong image for the. Let me change that first. Let's see if I can. Yeah, I can do that. I've got the wrong thumbnail going on here, so I'm going to change that real quick. That works. Okay. All right, so I'm going to plug in the controller, turn my computer on, start Mach 3, and then have the motor do something. I'm probably going to turn off the other camera since it's going to be blocking. All right, good. All right, that's not the one I want. I also need a cable to plug into the controller. So maybe what I could do, because I did experiments with the motor with a standard, like this is a 425 ounce-inch torque motor, stepper motor, and I did experiments already on one video I did a little while ago. I think it was a couple months ago, looking at the shielding issues or EMI issues with a signal wire that's run in parallel with this motor wire, and the results are really interesting. There is quite a bit of interference, but what I've also learned is from the Tuesday video on the interference with the router the router doesn't seem to have as much interference as the motor. So maybe in this video I can confirm that, or see if there's any difference, or if the motor is actually less. And I'm thinking about trying to create the experiments in a sort of more of a controlled fashion, like the experiments will be test it with B, and note those, note the results. Well, I mean, it's going to be noted on the video anyway, but understand the results, see what the differences are, see if we can sort of look at different ways to have this signal wire, you know, in what positions it needs to be in. So that will be looked at, and just sort of like running down, or maybe summarizing, and hopefully getting some feedback from chat on what they would like to see. Hey, you do it. Thank you for coming in. All right, so what I plan on doing in this, let's see, Mach 3, is creating a small G-code program to run the motor back and forth, but trying to make it in a way that it stops it in mid-acceleration. So let's see if we can do that. And what I'm doing right now is just opening Mach 3, and I'm going to be editing a text file. And this may, just writing the G-code may take a little while because I'm rusty with G-code. My G-code is, I'm well versed, but it was a long time ago. So a lot of that stuff that I did back then, you know, I'm not going to be able to remember all of that. But what I did do is mostly in Linux CNC. I did a lot of the programming, G-code programming in Linux CNC, because I needed a way for my pick and place machine to run under using a CNC controller. And Linux CNC is, at least for the G-code under Linux CNC is incredibly broad, and you can make it work just like a programming language. You can have subroutines, go-tos, calling functions, I guess you do, or you call it. You can also do loops. So it's really cool. And I'm sure you'd be able to do that with Mach 3 as well. I just don't know that instruction set and what the differences are. So let's see. All right. So this is where the program would be. But what I'm going to do is I'll test first the function of the motor, make sure it works fine, plug in the power supply, and yeah, just jog the motor just to see if it works. So we can start there. Of course, I'm going to be moving all kinds of stuff while I'm doing this, and hopefully there's no problems when I'm doing this. Okay, we heard the little thump from the motor. Also, what I'm going to do is I'm going to try to mount the motor so it doesn't do any weird movements, but also because of this phenomenon that another viewer was talking about, I was thinking maybe inertia also has something to do with it too, because if it's just like free flowing like this, it's not mounted, then a lot of the inertia is going to be translated in some kind of movement in the body of the motor. So maybe I just take a clamp and I just clamp it down, so a lot of the inertia can be handled within the motor, and then those inaccuracies can possibly be shown or expressed, or however you want to call it. So let me get a clamp here. I'm going to try to clamp it as close to the frame as possible, so I'm not putting any stress on the armature of the motor. I don't want to deform the body in any way. So thinking like this. All right, that should hold the motor. I can move it a little bit. Maybe I could put one on the front and then one on the back, because the back plate is also solid, so that would keep that from going. But I don't think this is not going anywhere. Let's see what happens. I should put the computer a little bit closer. And also having this close to this is going to be close to a power supply anyway when it's in. Did I move that? Yeah, I was talking about the controller being close to the power supply, but that's generally going to be what's going to happen inside of a standard CNC electronics. All right, so let me go ahead and try to move it with the, okay. All right, so now I need to definitely change the values, because the problem happened when it was going in acceleration. So acceleration is going to be 1, very, very low. And I'll go velocity 1000. The 6400 steps per may be too much. Maybe I'll just change that to 1000. I don't know what I have. I think it's set for 1600 per revolution, so maybe I'll just change it to 1600. But the velocity and stuff, it's going to be, this is really not going to be accurate. It's just to get a specific type of motion going on. So save axis settings. So let's see what happens when I ramp it up. There we go. Let's go all the way to the top. Okay, it still moves, but I think it's going a little bit too fast. We don't want the motor to stall during these experiments. So I'll bring it down to about 500. Yeah, that's better. All right, so what I want to do also is I want this. I probably should replace this with something more rigid so it's at least a little bit better understood where it is in degrees. So like when I'm going to 0 the X, so I can always go back to this position and see if it's changed in any way, like the angle has changed. So like, let's see, if I just move it. Okay, so that was a stall during acceleration. That was not good. Okay, it stalls during the acceleration. Low acceleration doesn't stall. Let's see. You can hear that little bump. And if you can't, let me know and I'll put the mic next to it. So at what point does it actually stall? Let's see. All right, I'm going to try to see on the feed rate. That was about 300. That was about 302. Let me go down to 300 here and see what happens. Okay, I got to the very top. I wonder if I can put 0.5 in acceleration, like a decimal. I should be able to. Oh, it's 3. It went up to 3 because I changed the steps per probably. Let me try 0.5 anyway. Yeah. Could I do 0.1? Wrong place. Let me see if I can get it so you can see what I'm doing also on the screen. Kind of. All right, so I'm going to go to, didn't want that, motor tuning, and I'm going to change this to, oh, it says 1.25, so I can't do 1. Huh. All right. Yeah, 1.25 is the smallest I can go. So let's go to 400 just to do some more tests. Save axis settings, okay. Yeah, I'm not getting any stalling yet. Okay. There is if you look at the torque curve of a motor, you'll always see the torque is maximum at sort of 0, and then it tapers down. But there is a place near the beginning where the torque just goes all the way down to almost 0 and then comes back up. So it's kind of like a spike, and that could be another place where it stalls during the beginning of its rotation. It looks like I'm getting no stalls now. Okay, so I guess I can write something small. All right, let's try this. I'm going to try, let's see, I'm going to try doing just back and forth with the X. Well, I want to go forward a lot, but then go back all the way because I don't want I don't want these bumps to be canceling out, going in the reverse direction and causing the shaft to appear like it actually is accurate. So if I just go in one direction, the air should be able to multiply, or at least add as it's doing the iterations. You Do It asks, I love that sound. When I built the MDF CNC with the plans you had, like forever ago, I got goosebumps when I spun them up. Yeah, that is a nice sound. Have you seen the music produced by stepper motors, like I think Star Wars theme? I think I think it was just a Star Wars theme. I can't remember the other ones, but I think there were other ones that were back in those times actually, which is kind of cool. I think somebody did it with one of my machines way back then. Okay, let's write a program. So I don't think I can create a text file here, so I'll just create it on the desktop. I'll create a new text file, text document, and I'm going to call it acceleration bump. And I'm going to need to save it as an NC file. So let's save as real quick. Make sure the text document says all files, and then put the .nc, and it should change it. Let's see. Yes. So it doesn't act as a text file anymore. So I'm going to see if I can get this closer so you can see what's going on the screen, and also probably change my ISO so you can actually see it and it's not overexposed. Okay, let me change the ISO, or ISO, I don't know how you call it. Okay, that looks good. Yeah, the Imperial March, that's wild. Okay, so the first thing, that looks somewhat clear. All right, so G, I'm going to use the Rapids, G0. So I'll go to 50, G50, or maybe I'll go to 10. I don't know how, let's just try that and see if it stops in the middle. So, and I can always change this on the fly as well. File, I should do this in the MDI first actually, shouldn't I? So let's just save this. I wish there was a way I can edit right from here, that would be nice. So I'm going to go to MDI first and see if this works. I'm going to 0 the X, G0, X50, or X10. Okay, it went all the way up. So let's 0 it again. G0, X5. Nope. I'm wondering if it doesn't work with G-code. X1, G0, X1. No, it's not going to work in G-code. It has to be jogging. It only works in jogging mode. It doesn't work in G-code mode. Oh, that sucks. Well, that's going to put a damper on things. Well, I'm going to try the experiment anyway, just with jogging, and I'm going to see. I'll just do an extended experiment real quick. So let me get comfortable in this chair. All right, I'm gonna. I need to turn that off. I just powered my phone off, so that's not going to disturb me anymore. Okay, so it would be nice to have something straighter, so this could be more accurate. Wonder if I should just put a coupling on there. So putting a coupling like this, maybe. Oh, you can't see a thing, can you? I'm thinking maybe putting a coupling like this here, and then we can really tell much better a more accurate representation of the angle. Let's see, hopefully I have the right Allen wrench. Nope, nope. Wait, maybe this was the one. No, but it still works. It doesn't really need to be that tight since it's not going to be coupled to anything. And I can barely get this on anyway. It's probably because of the sticky tape. All right, this one, this is way too small. Oh, this is the one. Nope. Yeah, well, that works. It doesn't really need to be that tight for this purpose. I could barely push it on anyway. All right, so since this is on camera, it can be, oh no, it's going to move. No, let me get that tight. Okay, that's good. This one will just be extra. Okay. Hey, Doug. Thank you for coming in. Appreciate the membership. Okay, so it is relatively vertical here. I guess what I could do is to even make that more evident would be to get something like a straight edge or something. Okay, that's relative. You know what? I could use a what do you call it? A spirit level, and then make it horizontal instead. Let me move it to horizontal, relatively horizontal. This is going to get in my way. Can you see that? Okay, so I'm going to move it a tad bit on either direction. I'm going to have to slow it down. Let's see. How do I slow this down again? Oh, I can use the tab and jog mode step. Okay, so that would be a high step. No, I'm going to change the percent here, 1%. We're just trying to find level for the beginning. So we can see that the bubble is touching the line. So that would be a good indication of this position. So I'm going to 0 it, X, 0X. And now I'm going to, I want to change it back to 100% for jogging. All right, so let's see. Hopefully I don't mess this up. If it stalls, then I'm going to have to do this whole procedure over again. Okay, so I'm going to go back to 0 and just to confirm that it's still at its place. Still exactly positioned the way it was. So this is at 0. So I'm crossing my fingers I'm not going to get a stall. All right, here we go. By the way, can you hear that little bump? Hey, Jojo, welcome. So we are at about 27 inches. So this could be a good indicator of Well, it's actually, it needs to be an indicator of number of times I do this rather than the number of inches. But I can't really tell that. I would have to start over numbering it. Okay, next time I'll count them, but let's go back to 0 and see if it still shows good. I think it's close enough. I don't see that much of a change. Yeah, no, it's exactly the way it was before. So let's do it again, but I'm going to count the number of times I do this. 14, 15, 16, 17, 18, 19, 20. So let's do 20 and see what happens. Let's go back to 0. It looks like it's in the identical place. All right, let's keep going. Let's try 40 this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm going to do 20 more, but I want to make a note that a lot of you may be wondering, does it really matter at what level of acceleration you're at? Because the torque is going to change. And there really isn't any way I can control that right now, because I tried to do the G-code option and it doesn't work. So here we go for 20 more. But that's a concern that I have as well. But if it doesn't show anything, any change at all, should we worry about it? I don't think so, but there is a concern out there, so we should probably still worry about it. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. So for the last 5 or so, I tried to go higher acceleration because you're going to have lower torque at those higher accelerations. So let's go back to 0 and see. Hopefully it doesn't stall while it goes back to 0. It doesn't seem like we spun it that many times. It's so funny when you go back and it's like, is it ever going to stop? All right, let's check it out. I see a difference, actually. I see a tiny difference. So there may be something to this, but it's really small. It's a small difference. Still shows level, but the bubble is more to the right than to the left. Could it be a creep from this? Like, did this move at all? I don't think so. So there is a difference. So we were moving it in this direction, but then when we stop the acceleration, it moves it a little bit more this way. It doesn't seem intuitive to me, but maybe that's the way it is. All right, so I don't know if this is appreciable enough to really be concerned about it, because like we all already learned, it doesn't happen through G-code. Although I could do like a quick G-code, just going back and forth, but that's gonna, if I do that, then, or I could do 2 forwards and 1 back, 2 forwards and 1 back, because I don't want anything to be canceled out. Let's just do that and see if anything happens. So I'll change my, let me see if I can show this on camera here. Hopefully it's not gonna be washed out. That looks like it's pretty good, actually. So I'm gonna edit with brackets. I could edit with brackets. I could open with Notepad. Here we go. So I'll make it go to like 2, and then 4, then 6, then 8. Or let's do 1, actually. Maybe it will work, actually. Let's see. See if I can get a closer look with the camera here. So I'm going to have G0x1, G0x2, 3, 4, 5, 6, 7, 8, 9, 10, and then I'll have G0 go back to 0. G0, X, 0. So 2, 3, 4, 5, 6, 7, 8, 9, and 10. So let's see what happens when I run this one. File, save, and let's find it in, well, let's see if I can show this also on camera. Hey Skeptic, how's it going? Yeah, I could tie an encoder to the motor. This is a quick and dirty thing. I'm thinking I want to do the quick and dirty because I don't really think it's an issue. It could be an issue. I'm sure it maybe is an issue. I just don't know what to think at this point. The encoder would definitely help, and that would be an interesting microcontroller project actually. So if I could write a microcontroller project program that counts the encoder pulses as it goes around, that would be nice. So maybe we could do that in the next one. I don't know, or after we do the OLED stuff, because I want to interface the ADC again and show that on the OLED. But it is kind of interesting how these two live streams could come together in some way. All right, let me file, load G-code, and I'm going to go to the desktop. Let's see, and I don't see it. And it's NC. Oh, I didn't save it as an NC this time. What the hell? Edit. Oh, there's nothing here. Then it was saved. What happened to it? What happened to it? Or maybe I saved it in another location. Let's see, if I do a save as, where does it save it? Desktop. Huh. I have to write it all over again. Did anybody? Oh wait, it's right here. The NC file. Why can't I find it? Oh, here it is. But it's an NC file. Why can't it open? File, load G-code. Oh, tap file. That's why. Let me change this to NC. Okay. There we go. All right, so we have our little file here. X1, X2, X3, all the way to X10. But it doesn't go back to 0. That's weird. Did I not save that? Let's change it. Edit. Yeah, G0, X0. That's weird. Let me put let me enter that. Maybe that's, couldn't read it. Save. Oh, and I need to unload it here. Close files, save as, and go to 0. Let me add that there, save. Okay, load G-code again, NC, that's good. It doesn't have the last file, why not? That's weird. All right, there's something going on here. Let me unload it. Oh, maybe it's saved as a text file. Yeah, it's saved as a text file. All right, close files, edit, file. This is what I don't like about the notepad files. It automatically saves as a text file. No, I don't want that. So file, save as, text document, all files, .nc. All right, Skeptic, question 1. Are you testing if interference may cause some issue? In this case, no, because I'm addressing a viewer from last stream on Thursday. He is saying that during an acceleration, there's a little bump. He is seeing there is it causes an error in the motor's rotation and causes it to lose steps essentially. Question 2, don't most CNC machines rely on feedback? Most of them, I guess most of the hobby ones, probably not. Most of them are open loop systems. The ClearPath and other companies, they do sell servos that you can connect to machines or use for the actuation of machines. But lately, at least in the past 3 or 4 years, you're now able to buy closed loop stepper motors, which are, in my opinion, better for the price. Because with stepper motors, you have exact stop. There's no PID transient response at the commanded location. So I like it, but the PID transient response may not be an appreciable issue anyway for a lot of machines, because the technology has gotten so good over time. So in this case, it's just an open loop system, and I would say most hobby machines are open loop. They're just, it's a computer commands it to go to a location. The stepper motor, because it's digitally stepped, it will only go to the number of steps you tell it to, and stop at that particular place. It doesn't have any PID control at all. It's just a step. Two coils control a sort of DAC-based controlling of those digital to AC. So you'll have like a stair-stepping waveform to control the steps of this stepper motor. All right, so let's see if I can load it in. Okay, here we go. Please have that last line. Let's see. Yes, okay, good. So I can do a cycle start and see what happens. So let me change my camera location here. Okay, that works right there. Yes, then skipping is very possible. That is absolutely true. But that's why we are trying to determine, because if your motor has high enough torque, you shouldn't have to worry about it, because there's a safety factor as long as you're within that range of its torque. So most CNC machines, you'll have projects, jobs, whatever, that'll never have a problem, even if it's open loop. Closed loop, it is. I was actually talking to a customer yesterday about this. Closed loop is just peace of mind. So if the job screws up in some way, you lose steps or whatever, the job will stop. Or, well, in the best case scenario, it keeps going and it recovers those steps, or it makes up for those steps, because it's always trying to get to that commanded location. Worst case scenario, if it just can't do it, then the machine stops and it saves your work essentially. But then you have to go through a homing procedure, probing procedure and stuff, and you still have to, continue the job somehow. Yeah, measuring position, absolutely, for sure. Measuring the position is the best for when it comes to closed loop, for sure. So that's where, like, making a program on a microcontroller would be kind of interesting, and to actually do more measurements. But then we still have the problem of, okay, at what point of acceleration do we do these measurements, and how can we make it so it is repeatable, like getting the same, having it stop at the same part of that acceleration. And this is where we're seeing if at least G-code can do that, but I don't think it's going to be able to. Let's try it. No, it doesn't do the bump. So we can't do this in G-code. Hey CNC, how's it going? Thank you for coming in. Always a pleasure to see you. All right, so we cannot get the same effect using G-code. We have to do it manually. That really, really, really sucks. Or it sucks in a testing environment thing, but it doesn't suck in that the problem isn't present during the G-code running. So the only way we can replicate it is just doing it by jogging. So we've already done it 40 times, or 40 steps. Should we continue doing this? I'm gonna ask chat to see if we should continue doing more testing on this, or go back to the shielding and discover more shielding anomalies. I vote go back to shielding. Or potentially, if you do have a suggestion, what do you think I should do next? I'm going to increase my ISO so you guys can see what's going on here, while you guys have a chance to state anything in the comments. Yeah, up to me. Okay. All right, well, I'll go back to shielding then. All right, cool. So we're going to keep our setup here. We have a motor. The motor, oh my God, this is hot. I'm going to change this to half current for idle. This is definitely hot to the touch. I can't really keep my hand on it. It's normal though. That's actually something that a lot of people ask me, like, should I put heat sinks on my motor? And I say no, but you can if you want. You can put a fan on it or whatever. But that's just the coils getting hot because of no movement. If it has movement, then that energy is going into the movement rather than heating up the coils. So there is a setting for the dip switches. Switch number 4. Let me see if I can give you a better look at that. It's going to be hard to see. Okay, right here. It says switch number 4, off is half current, on is full current. And that is in its idle state, unless somebody can correct me on that. But from what I know, this is while it's not moving. And this is important because some machines use rack and pinion, ball screws. Those have very low friction, and if it's like on the z-axis, you need it to stay up and not crash to the ground if half current can't keep it. So you might need full current, but half current at least keeps a stable machine or keeps it in a particular position while it's not moving. So let me change that. And right now it is 1, 2, 3. It's definitely on. So I'm going to turn that off so we don't have overheating going on here. You probably didn't see that. I changed the, let's see here. See number 4? It's up now. Puppies, thank you for coming in. Welcome. Shielding, maybe talk about advantages, disadvantages of connectors. I've always wondered about this or that. There's a heart next to the screen that I can't read some of the comments. Yeah, connectors is connectors in terms of connecting on a cabinet, like a motor connector going into a cabinet. Is that what you're talking about? The connector is generally where it's going to be connecting to shielding as well. So the connector itself in a lot of cables will be shielded. So let me show you an example of that. I'm going to be getting into this a little bit later, but here is a set of cables. These are very high. Well, these are cables for the Spinology spindle, and these are fully shielded. The cable. Let's see if I can give you a closer look here. These are very expensive cables too. These cables are around $200, around that, maybe a little bit more. So the cable itself costs more than Chinese spindles. So this connector itself connects to the shield, and this is most likely double shielded here. You can see the shielding on this part of the cable, if I can get it. So this is probably one of the shields right here. This is a braided shield. And then you can see another shield here on this smaller cable that's inside of it. And I believe this is the temperature sensor. I think this is a temperature sensor. Yeah, and we'll be getting into that too in a future video. So this is the actual motor cable for the spindle. So it has, I don't know if you can see inside, it has 3 big connectors and then 2 smaller ones. There's a lot more actual connectors here, but only 2 are being used on the smaller ones. And then you have a middle one that's ground, and that's going to be also connected to the shield because obviously this connector is shielded. So the 3 connectors is for U, V, and W for the spindle. And we can also look at this with EMI as well. So hopefully no EMI is going to be escaping this, or not of a sufficient amount to make a difference. Okay, and then we have the other cable, which is primarily sensor information. So this will tell the system if a tool is present, if a tool is not present. I'm not sure if it will have a RPM sensor in there, encoder. I think it may have an encoder. I have to go back and look at my video to see what I said in it. But these cables are pretty insane. And you can see the shield here. So for the question about connectors, and I'll look at the comments now to see what you guys were talking about. Going through cabinets, yes, okay, good. More about failure points in the connector itself. All right, hold on a second. I'm trying to see the comments because I have this, if you look, you can't see it. Of course, I'm connected. Right here, you can see there's a heart, and I can't read what's in this heart. But if I turn it around, but I'm not getting my, because I had it in a certain mode that it wouldn't allow me to turn it around. Let me see if I can fix that. No, it doesn't want to turn around. Okay, well, I'll try to read the comments. All right, what is typical, the standard for CNC connectors that attaches to a cabinet? I noticed that is locking. Yeah, that one is locking. Yeah, well, the chat goes up, but I don't get much chat, so I have to go with what I got. Deal with what I'm given. All right, so yeah, and let me address the connectors again. I also use other connectors. See, if I don't have a metal connector, let me see if I can find these connectors. I love. These are Speak-On connectors, and they're used for audio equipment. CNC might know a little bit about this one. But I love these because it's plastic, obviously, and of course that's going to be an issue potentially, but maybe it's a benefit, I don't know. But if you look at the connectors, these are just screw terminals, and they work really well as long as you make sure that they're securely fastened. So what I do in this case, because I do use shielded cable in, I can't remember how to put this thing in. Yeah, no, it was like this. Because this is plastic, I have and you probably see this from my other videos on putting CNC electronics together. I'll take the shield out of the cable that's coming in, and I'll take the shield and I'll bring it out before it gets to this point, and then I'll put a terminal on that. And then I'll put a screw on the cabinet and screw it into the cabinet so it has an electrical connection. And I always test those for continuity to make sure that it has a good connection to the cabinet, which is already grounded. Thanks, CNC, for the membership. Now you're green with a star. I got to change the little icons. I want to change it to the icon of the business for branding purposes. All right, so that's what I do with connectors if I don't have the possibility to shield the actual connector. And the metal housing of the connector, does that also emit EMI if it collects the EMI? You know, that's a question that I have, and that's why we do these experiments. So, as I said earlier in this video, I want to test. See, now this is not as hot. I can keep my hand on it. It's warm. It's starting to hurt a little bit, but I can still keep my hand on it. So compare the shield or the EMI from this motor, compare it with a router. Because of course there was a question, you know, the shield wire, why do these tests if you don't have it inside of the CNC machine? But I don't understand why you'd want to put it inside the CNC machine, because you're going to get all kinds of EMI and you don't know what is causing it. So why not do the test with the individual components instead? And then at the end, we can do the test with the CNC machine. So that's my thought. And let me know if you have any other thoughts on that. So let me get a couple. So I'm thinking the longer the cable, the better. So let's go ahead and use something like this. So we'll do it again, just a bare wire, and we'll put the wire in line with the motor cable, and we'll do it in line with the router cable. But I also want to try both routers, because my guess is this is going to be a little more noisy. It's a cheaper router than the Porter cable, so we'll see. I don't know. Although this is a bigger and more powerful router, so you'd think that there would be more EMI because of that. So what are your thoughts now before I do these tests? Is the little stepper motor going to be more of an EMI emitter, or will it be the routers? Let me know what you think before I do these tests. So we'll try a single wire like we did before. This is Christmas time wire. It's not going to be easy. It's going to get tangled up. No. All right, good. Didn't get tangled. All right, so we have a very long wire. This is probably the size of a wire that would be in the CNC machine. All right, big long wire. And oscilloscope. Oscilloscope. Some people call this a scope, but if you do that on Joey's live stream, they would think it's a microscope, because Joey doesn't have an oscilloscope. It's getting cluttered here. I'm going to change my power to another circuit so I don't power down the whole live stream. Ouch, I just hit my knee. Okay, all right, different circuit. All right, let me turn this on. Skeptic. Brushed motors will have more EMI. That's what I thought too. Okay, so we'll test it. Puppies, more power, more RPM, less shielding with router equals more noise. Okay. You Do It says it's a great scope, love mine. Well, I mean, it's cheap. It works, it's been working for years. But it only has 100 100 million samples per second. So that's the drawback on this one. Seeing the level of technical proficiency that Joey has, he's skilled and not using is surprising. Yeah, he says he doesn't have space for it, but yeah, maybe he doesn't. And you know, if it works, it works. If what you're doing works, keep doing it. I like what Joey does. I'm going to make sure that these wires or cables are not anywhere near each other for now. Okay, I'm going to go with this first. So what I'll do is I'll take this wire and I will put it in parallel with this motor, making sure that I get as much coverage as possible. So I'm going to get a bunch of these clips. And these clips, you think these are helping or hurting shielding? To minimize EMI, you want to keep them away keep wires away, or you want to make sure you do it in intersecting. But intersecting, we also found out that there's still EMI, but it's not as much from that other video. Let me get some more. Binder clips. Nice shot of my head. This is going to be difficult. Okay, that's good. And first, I'm kind of interested to see if we get the same atmospheric EMI that we did last time. The idea of step and direction signals, because those are always going to be right next to the controller, and it would not get anywhere near these unless you or the person that created the system created a rat's nest in the cabinet with motor wires and signal wires going all over the place. But it's generally not done that way, and I shield the internal wires anyway sometimes, most of the time actually. So this isn't really not. And I don't want to twist it around the wire either, because that can help communication and not allow us to seek EMI, because we're trying to find EMI. We're looking for it intentionally. All right, so this is the end here. It's going to be hard to get a good, because this is a long wire, and the router has a short cable, a short wire, but I'm going to put a lot of it right next, so hopefully that will help. All right, let's see what's going on in chat. I haven't used my scope in a long time. I need to relearn how to use it. It was a cheap. Well, you can watch the way I do it, because I don't know either, and we'll learn together. Coil the wires as tightly as possible. Create a super magnet. Skeptic, if you are running them in parallel, whichever draws more current will be picked up by the other, as they will be coupled. All right, we'll see. The rain harvester, hey, thank you for coming in. I appreciate it. For limit switches, did you ever try the resistor capacitor trick? We did in the last, or in the Tuesday live stream, we did, and it was amazing. It actually worked. The capacitor specifically, we used a 100 microfarad capacitor, and it worked. It flattened out the waveform perfectly. We didn't even find the atmospheric sine wave anymore either. But that would work really well with limit switches. It wouldn't work so well with a pulse. It could work with the step, I mean, for the direction signal, but it wouldn't really do very well for the pulse for the stepping, because then you're kind of flattening out the curve a little bit. But I haven't tried that, so I don't know. Maybe the capacitor is fast enough to allow that to be maintained. Okay, so CNC, for someone just coming into the stream, is probably wondering, what in the world are you doing? You do it, yeah, that's cool. Rain harvester, never considered that for limit switches. By the way, rain harvester, I think you started watching my videos from the initial shielding video. I can't be certain on that, obviously, but that's when I started seeing your name, and I'm glad you're here. Yeah, same step direction. It needs to be very well separated, in my opinion. But like I said, these are all opinions. I don't know what to expect. I'm not an expert in shielding. I guess doing 100 of these, maybe I'll become more of an expert, but still we're seeking EMI. We're just trying different things and seeing what happens. All right, I have my oscilloscope. I'm going to keep it at because this is going to be we're still doing the motor right here. This is going to be, what do you call it? yeah, I'm not connecting this to a 24 volt source or anything yet, the actual wire. I'm just using this as an antenna. I just want to measure the antenna idea of it. So like, what is it picking up? So I'm going to connect it to this end right here, unless anybody has any other thoughts. So I'll connect it to this end. So we are essentially picking up a lot like radio signal, essentially. So this is just, I don't know if I should plug this in or not for the ground. We'll find out. So let's see what happens when I move the motor. And first I want to see what happens with the signal on the oscilloscope, and this is a lot of glare, so you're not going to be able to see anything, are you? Still glare. All right, let's try. The more I move it, okay, that might be a little bit better. And my ISO may be a little bit too high. Let me bring it down. Okay, that might work. Let me see where the waveform is. Okay, here we go. Ah, there's the waveform we were looking for. That's the atmospheric thing that I was talking about before. So we have it on 2 volts per division. So that's a lot. So this is a half a volt almost. Peak to peak is 1.8 volts. That doesn't make sense. Oh, that's peak to peak, so half that. So that would be a whole volt. What? Yeah, that's about a whole, that's almost a, yeah, because it's 2 volts. What the waveform, oh, let's change this, yeah. Okay, so that's not really a good sine wave. Well, let's see what it looks like with the trigger. Okay, so check that out. That's quite large. 60 hertz. Where do you see that? The period is 16.66 milliseconds. So does that translate to 60 hertz? Probably. 16, what's 100 over 16? Is that how you do it? No, that's 6.25. Oh, that's 1,000. Yeah, 62.5 hertz. So, yeah, 1,000 divided by 16.62. Let's try that. Yeah, we got about 60 hertz. Check that out. So yeah, so this is coming from where? From my computer, from, I don't think it's my computer because we had it last time without the computer on. What appliances? There's nothing going on here except for my computer back in the, well, my computer kind of far away. I have no washing machines or anything going on. I don't have any appliances in here. I don't have my AC on. Maybe my, yeah, maybe like my printer is idling and my printers are idling. I have 2 printers. I've also got my computer that's obviously probably like a 400, well, more than 400 watt, probably like a 600 watt computer power supply. So that's, yeah, that's interesting. So we should, fluorescent lights. No, they're not on. They're off. Let's see what happens if I turn them on. Just turn them on. No change. I don't want to turn off my computer because I'm live streaming. So it is what it is, and we are going to use it in our scenario because we are seeking EMI, and this is part of why we need to shield. So let's do the, let's connect a capacitor first and see what happens. This one is this is a 100 microfarad here. I can't really see it. This is not the right lens for that. Yeah, the oscilloscope itself, you think, could be one of the culprits, obviously. Yeah, it's a cheap oscilloscope, so, you know, maybe. Foil is an interesting idea. I don't know if that's going to be like a direct type blockage. I don't think that's going to do anything, but let's go ahead and see what happens when I turn on the motor, because if this is connected to ground, we know that that's going to go away. If I connect this to ground, I know that the waveform will generally just go away. Or what I could do is connect it to the input controller. I could put one end as an input to the controller. That could be, I mean, that would be in the, well, let's do the first test. Let's not get too complicated. Let's not go overboard here. Let's do a test real quick just with the motor going and see what happens. Okay, how do I change the time base to capture high frequency spikes? I'm not really sure how to do that with this oscilloscope. Remember, I'm not very smart when it comes to oscilloscopes. So if you guys can help me out with that, that would be cool. Otherwise, I'm going to show what happens in this scenario when I turn on the motor. Although the motor is, yeah, the motor's not connected. So once I power the motor, immediately we should see something. So I'm going to go ahead and power the motor and not move it, because it is holding its own torque, so we should be able to see something. And if anything explodes, it'll be on video. Oh, look at that. Check that out. So it is picking up all of the coil. So if I change the, so now we're seeing what the coil is actually, the pulses of the coil essentially. And I have it 5 volts per division. So that's an entire 5 volts. So obviously this is not the scenario we would be using a limit switch. So we're going to have to plug it into the controller, I think. Well, that's wild. It's cool to see that we can check out a coil without actually probing the coil itself. We could just put a wire next to it. This could be a really good place to test as I remove the wire one binder clip at a time to see how it changes. What I could do is I can make this 2 volts per division and see if it gets smaller as I remove the wire from it. Would you like to see that? I think that's a good test. The motor cable is shielded, but I don't think it's plugged in. No, it's not actually being shielded at the moment. And I did that on the last. I didn't want to shield it in the last because I'm trying to find EMI, so I'm keeping the shield open. It's basically a transformer. That's true. Basically, it's high frequency. Yes. Doesn't need much turns. Yeah. Okay, you do. It says set a trigger for spikes above the typical waveform height. We're not going to see spikes, I don't think, in the stepper motor. We will see spikes with the router, which we saw spikes before. I don't think we're going to see spikes in the stepper motor, but I can definitely bring the trigger up. I'm going to have to lower the. So if any spikes are going to happen, it's just going to be from the beginning of this little transient response here. Oh, you're not seeing anything, are you? I have to remember to do this. All right, so let me do that over again. So I had the trigger somewhere around here so I could show the waveform, but it was up here at the time. So to see any spikes, I'd have to put the trigger back up here somewhere. And you can see that it stops triggering if I slowly move it. So I'm getting this spike here, the one that comes up, and then it slowly gets down to, it relaxes down to its square wave. So I'm getting this little spike here. So the stepper motor, I don't think we're going to see a spike. We will see it with the brush. All right, so let's take away some of the wire, because remember we don't have any of this grounded or anything. So this is just an antenna. So as I remove it, I want to be able to show that removing and the oscilloscope at the same time. I'm going to have to set this up on my computer so I can do. So before Thursday, hopefully I'll have that done. So I'm going to take off this one right here, the one closer to, or should I do it from the motor side? Maybe I should do it from the motor side. This didn't change anything when I move this. So when I move this around, nothing happens, the probe and the wire. So if I'm going to start removing it from the motor side, from the driver end, or the motor end, from right there. So I'll take this one off, but I'm going to take it off while I show the oscilloscope. I think that's going to be better, and I'll just say what I'm doing. Okay, I'm removing the first one, and I'm going to pull it away. It definitely changed, and this is just 5 inches. 6 inches, 7 inches, yeah, 7 inches. So I'm going to go ahead and just bring this back down. I should be measuring this, but I don't see where the trigger is shown as a value anywhere here. But I do have a peak to peak, so I have 13 volts as a peak to peak. Okay, let's take off the next one. This will remove about, well, I can actually measure this. So the first one was approximately 6 inches. Now I'm removing a full 19 inches away from the motor. And we can still see peak to peak is 12, around 12.6, so it did go down a little bit. Let me remove the next one. Okay, now it's about between 10 and 11, so it's definitely lowering. So let me measure that one. So now we have 31 inches away from the motor cable. All right, now let me take off the next one. All right. So now it looks like between 9 and 10 volts peak to peak, and this is 42 inches that I released. All right, I just released the next one. Now we're at 9.4, still between 9 and 10, which is, it's getting harder and harder to measure this. We're at 52, so it's about 10 inches per. So I'm just gonna use that as a guide. I'm taking the next one off. So this is gonna be about 62. We're down to 4.2. Let me bring down the, oh my God, no, you don't wanna be here. Oy, oy, oy. The cat was getting too close to the live wires. Okay, so let's take off the next one. This should be about 72 inches off. Now we're down to 3.6 to 4 volts. I'm gonna take off the next one. We're probably looking about 82 to 85 inches. We're down to 2.9, 3.12. Take off the next one, about 100 and, I'm gonna say 100. Hey, this is down to peak to peak. Oh, it's up to 4 again. No, 3.6. If I put my hand closer to it, it jumps up. I'm actually have an antenna myself, probably. So still about, it's still a little bit high, so that's weird. That's unexpected. I'm gonna take off the next one. And this is about the last one. So we got one. Let me show you what we have left. We only have one left, and this one is hanging off the ground, and also the probe is hanging off the ground. So we just have one little bit connecting to the cable. Now what I'll do is I will release the last one, and it should just, the waveform should just go bye-bye. So let's see. I'm releasing it. I'm putting it on the floor. So now we don't see anything. So that was a useful experiment. Let me increase this. See if we can still see something. We can still see something here. Even though the wire is fully away from the, it's on the ground actually. So it's down here somewhere. And you can see this is right next to the motor. So let's see if that makes a difference. The actual probe itself. No, I still see in fact, the waveform is going up and down because I think it's this wire. So this wire, I can't see a thing. I'm moving this wire closer and farther away, and it really changes. And I'm going to show that to you on the oscilloscope here. We're not talking about a lot of movement because I have I probably have it like 5 volts per division. No, 200, I'm sorry, 200 millivolts per division. So it's going to show very sensitive stuff. So if I put it closer, you can see it increases and it decreases. If I lay it right on top, it's just crazy. So I have to take it way away from the motor wire to get rid of that signal. Well, to eliminate it as much as possible. We're still getting peak to peak about 1 volt. So that's a lot. All right, let me look at the comments. You do it. Now, okay, we already saw that. Puppies, that's where the cable is not shielded. Yes, that is true. Yeah, when we're taking off the first set, the first part. But the whole cable is not shielded anyway, so it won't matter. You have Vmax. Skeptic says you have Vmax. I'm not sure what that means. Skeptic, oscilloscope's probe is enough to pick it up if it's next to the motor. That's true. Yeah, Kitty. You're an antenna. Wait, you are the source of the 60 hertz? Maybe I was the source of the 60 hertz. It's my heartbeat. Put the probe next to the motor. Yeah, let's just the probe. I'm going to take the wire off actually because that's going to be interfering. Okay, let me try to put this on video as well. But it's not that much. Let's see if I can go down and still see the oscilloscope at the same time without glare. And try not to get electrocuted at the same time. That's not going to show very well. Maybe it will. Okay, that's good. All right, so I can still see that, and I'll put the motor in frame as well. And see if I can, oh, that's pretty good. All right, so here is the probe. So let's go closer. Well, the probe wire is also close to it. So let's go closer and closer. All right, let's try the housing. So the housing, pretty big. the wires themselves. Yeah, we can get it on the wires also. And this is peak to peak about 246 millivolts. Okay, so what if this is already grounded to earth. I'm not sure if this is going to work with a capacitor, if I put a capacitor between these two, but I'll try. I really do want to put this on the controller so I can do the test with the DC minus and the capacitor like I did last time. So this would essentially be the positive. This would be the positive, the probe would be, and then this would be negative. So now you can see that it definitely changed. It's not as noisy at all. So the capacitor is filtering, or it's flattening the curve. So the capacitor, even at the probe, is making a big difference. It did show something, but I think I shorted the two while I was doing that. So I don't see anything. This is normal as it is floating. Yeah, it's floating. This is this part of the experiment. We're doing a floating experiment. We're doing an antenna experiment. Any load will kill it. Jabari, hey, thank you for coming in. I want your help in programming STM32 for building a keyboard mechanical. You can do it in video or live if you want, sir. Come to the STM32 live meetings. That's on Monday, Wednesday, and Fridays. So tomorrow I'll be doing some STM32 stuff. We're still looking at the OLED, so we'll introduce the idea, I guess, to chat to see if they would also be interested in that, and we can move on from there. This is what I was saying. Anything between probe and ground will kill the noise. Yeah. Yeah, well, in this case, it's obviously a capacitor. If we put the ground on this, of course, it's going to just bring this to ground, so it's just going to be a line. But this we found from the other video on Tuesday. You can see it's got a, look at that. That's interesting. That's the floating thing. You can make a musical instrument with this right here. So we did this on Tuesday. We actually put it on the controller and we tested it with a capacitor, and the capacitor smoothed it out, but we still got a good signal, a high and low signal from the limit switch. And now we can do the same. Do you want to do the same thing with the router to see what the peak to peak is? We can do that. So now I could probably turn off the motor because I don't want that interfering anyway. We're at 3 o'clock, so I'll do 10 more minutes. So we'll try to do one test with the router on and see what happens. I'm going to go ahead and plug it in. Hopefully it's not on. Let me just make sure. It says off. Good. Okay. And this one has only two. Let me show you. Can somebody tell me why there's only two of these on here and there's a metal housing? I know that ground is shared with neutral in most houses, but wouldn't it make sense to have a third prong here for ground anyway? And it would be grounded on the body of the motor, because I'm going to be holding it while I'm doing these tests. My address is on my website. If I fall over, just call EMS and look for my address on my website. All right, I'm going to turn on the motor just so you can understand the sound. So if you have headphones on, now would be a good time to turn them, I guess turn the sound down or something. I'll give 5 seconds. 5, 4, 3, 2, 1. Most of you may remember this from the last live stream, how loud it was. Ujawal, thank you for coming in. Can't read your writing, unfortunately, I'm sorry. Can we shield shock? Don't know what that means. I'll need some elaboration on that. Puppies, I was told that third prong is not needed. Yeah, if the motor was double insulated. Okay. Saves the company money. Nice. All right. The ground prong also helps, I can't read that last one because the heart is in the way, from bridging if something falls on the plug. Okay. Interesting. All right. So you know what it sounds like. So that's what you can expect. I'm going to go ahead and I'm going to try to get everything in the shot if I can. I'm going to put the router a little bit closer to the oscilloscope. Nothing going on there. Just to have it on the probe. All right. And I have the cord going to the the electrical plug. So the little green wire, I want to put some on the body. So maybe I'll just get some tape. If I don't get time to do this experiment, I'll keep the tape here, and I'll just stop it at that point, and we'll continue on Thursday. Maybe I'll just keep this here because I'll have other wires anyway. And so we can plug this into the controller as well and do the same tests. You can see the mess that I have, my messy shop. We should definitely see a spike at least 60 hertz when we turn this on. Or while it's plugged in, right? So it should be still showing 60 hertz because it's plugged in. So we should get an extra amount of noise when we turn it on because of the little bit of wire that's next to the housing and potential just the EMI going farther away, I guess. I probably shouldn't be completing that or going all the way around. So I want to take it off at one point. This is actually pretty long. This cord is long, so I'm using almost all of the wire. I'm sure some CNC machines have the limit switch wire right next to the cord of the router. Some CNC routers. Okay, I'm going to leave this last bit untaped. All right, let's see. Do we see any? Well, we won't yet. Let me plug it in. Should I put the probe at the far end or at the near end, like right here? Maybe I can do both tests. Let's try it at the near end first. What can get tangled will get tangled. So this is definitely going to show something because I got the probe right here too. I think it's probably better to have the probe on the other end. Oh, look at that. So we have it at 2 millivolts per. So we're looking at a sine wave. A very nice sine wave too. So let's bring it to, that's 500. Let me slow it down. Oh yeah, check that sine wave out. Well, that's actually kind of not a sine wave. Yeah, it is. So that's the cleanliness of what you would expect on an American circuit, probably. All right, let's see. Yeah, far end, I'm thinking that too. Let me see what happens with the far end, see if we see the same kind of anomaly here. Hopefully this is long enough. And this is just from the wire itself, so because the router is not even on. Yeah, I still see it. So it's the same, but we will see maybe a difference with the motor going on. So what is the peak to peak? The peak to peak is 5.7 volts. Last time we saw a big spike. So I'm going to change this so we can actually see the spike. I'm going to change the trigger level to just above this. I'm going to change the volts per division way down. 5 volts. That's 5 volts per division. It's still showing a lot, this antenna. Okay, I'm going to turn it on and see what happens. I'm going to put the trigger way up, actually. And I'm going to move the position of this all the way down so we can see something. It will probably happen in both directions, but I'm more worried about positive than I am negative. But I could be wrong. All right, I am about to turn on the router. So I'll do that in 5 seconds. 5, 4, 3, 2, 1. And this is what happened in the last experiment. We saw nothing. But we saw something in some experiments, but it was a shorter wire. Should I put the trigger closer to the waveform? I can put it like right above the waveform. Let me do another. Should I take my hand away? Maybe my hand is causing some shielding. 5, 4, 3, 2, 1. Okay, nothing. So let us ponder this situation until Thursday. Let's see what we can come up with until the next live stream, because I'm very bewildered why I'm not seeing any spiking going on when I turn the motor on. And we know that it's connected to the probe. We know that it's getting the noise from the AC. So what could this be? Why aren't we seeing the sparks from the brush? So I'll leave this as the cliffhanger for next time, and we'll try the other router as well. Maybe it's more noisy. Maybe I don't think this is brushless. I think it's brushed. but we'll find out next time. I'm going to keep the live stream rolling, but I'm going to turn off my mic so YouTube can capture the tail end of this video. So I want to thank everybody for coming in and participating and giving me your thoughts, helping me out, guiding me. I am extremely gracious, or I have a lot of gratitude for that, and I appreciate it. So for anybody coming in and anybody coming in the future, I want you guys to help me out with these experiments, have fun with these experiments, and see what we can learn. Thank you so much. And Roms, thank you for coming in.